Let us finish our discussion of the pigeonhole principle. Please take a look at this problem. So in number 4, we have 8 numbers. Prove that if 5 integers are selected from A, then at least one pair of integers has a sum of 9. Remember, we have to use the pigeonhole principle. Guys, take your time, think about.
Sorry, is it that you have to count the number of pairs that add up to 9? And it's 4. So 5 is one more than 4. So that if that's one more than the pigeonholes, and it has to at least have 2 that have sum of 9, is that right?
Yes, absolutely. And which pairs would you form?
1 and 8, 2 and 7, 3 and 6, and 4 and 5.
Absolutely. So let us consider 4 pairs. 1, 8, 2, 7, 3, 6, 4, 5. Note that in each pair, the sum is 9. 1 plus 8 is 9, 2 plus 7 is 9, and so on. Observe that we have 4 pairs, but we have to select 5 integers. Since we have more integers than pairs, there will be 2 integers from the same set, which means the sum of these 2 integers will be 9. Again, without reading the solution, prove that given any 12 integers, we can choose 2 of them and such that their difference is divisible by 11. Any ideas here?
Because 12 divided by 2 is 6 and 2 is smaller than 6. So we can say that there will be 2 such integers whose difference is divisible by 11.
How do we use the fact the difference is divisible by 11?
Because 11 is smaller than 12.
So what?
By pigeonhole principle.
What if we say they will be divisible by 10 or 7? Will this approach work?
No.
You see, here it looks like you use pigeonhole principle twice. 11 is smaller than 12, then you divide 12 by 2. It's a little bit confusing. Okay, so here's what we do here. Let us consider any 12 integers. And let us divide each of these integers by 11 and find the remainder. Note that the remainder, when we divide any integer by 11, is either 0 or 1 or 2 and so on 10. And now observe that we have 12 integers. So there will be 12 remainders between 0 and 10. Since we have 12 remainders between 0 and 10, there will be 2 integers that give the same remainder. If we subtract these 2 integers, the remainder will be cancelled. Therefore, the difference will be divisible by 11. Next, how would you solve 6? A plane is colored blue and red. Is it always possible to find 2 points of the same color exactly 1 inch apart? By the way, may I ask a question? How do we use the fact that they are 1 inch apart? What if instead of 1 inch, we have, say, 3 inches? Folks, any ideas?
Maybe you could make the 2 different colors, the 2 pigeonholes, and the distance, I guess, the pigeons.
Okay, so colors are pigeonholes. Okay, next.
Let's see. Well, I mean, the 2 points, I guess, would be the each point would be a pigeon then. I'm not sure.
Okay, but now we have the same number of pigeons as pigeonholes.
Let's see. Well, so I was gonna first say that it was the distance being 1 inch, which is, I guess, less than 2.
Okay, so what if instead of 1 inch, we have, say, 3 inches?
I'm not sure then.
Let me ask you a question. If there are no red points, all points are blue, is it possible to find 2 points exactly 1 inch apart?
Yes.
Yes, why is that?
If it's all blue, then, and no matter where you look on the plane, there's going to be a bit of blue 1 inch away from the one you're pointing at.
So just pick 2 points exactly 1 inch apart, correct?
Yes.
So if it's all blue and we replace 1 inch by, say, 5 inches, will it always be possible?
Yes.
Yes, the answer is yes. Just pick any 2 points exactly, say, 5 inches apart, correct?
Yes.
Now, if, say, in the middle of this blue plane, we have a huge red dot, is it possible?
Yes.
Why is that?
If you're in the red dots, then 1 inch, if you go 1 inch apart, basically inside the red dot, there's any points in the red dot, there's going to be red 1 inch away from it.
Okay.
And outside the red dots, if you pick any points on the blue, then there will be blue 1 inch away from it.
Okay, wonderful. Now, imagine that we have a gigantic chessboard that consists of blue and red squares. And squares are really small, much smaller than 1 inch. Is it possible?
I think yes.
Mm-hmm. And why is that?
For the same reason as before, if you pick one of the blue dots, then 1 inch away from it, I'm picturing like you're sweeping in a circle with a radius of 1 inch. Eventually, the end of it is going to hit another blue dot.
Very good idea. So pick a point of some color, either blue or red, correct?
Yes.
And then draw a circle around it with a radius. Which radius?
The 1 inch.
1 inch. All right. What do we do next?
If there is a point of the same color at some point on the circumference of the circle, then it's true.
Yes. Then we are done. If there is a point of the same color on the circumference, we are done. If not,
then this statement is false.
are you sure?
Yes, because it says always possible. And if it's not true for one of them, then it's wrong.
Any other ideas? So you see, we are free to use any points, not just the center. So we pick some point, say red, we draw a circle around this point, and if on the circumference we have another red point, then the statement is true. But now assume that on the circumference we do not have red points. This means that all points are blue, correct? So what?
You could span 2 points on the circumference of that circle. They're 1 inch apart.
Absolutely. Let us use 2 points on the circumference that are exactly 1 inch apart. But my question is it possible to find 2 points on this circumference 1 inch apart? How to prove it?
I'm confused what it means by 2 points of the same color. Like,
1 point is blue, the other point is blue. 1 point is red, the other point is red.
right, but so when you're painting a plane, you don't like paint it with a bunch of dots everywhere. You kind of.
Very good point. Think about a plane as about a collection of points.
So you're
Right?
saying that the plane is like colored blue on one portion, like half of it's colored blue, the other half is colored red, for example.
No, since we can think about a plane as about a collection of points, let us assume that each point is either red or blue. That's it.
Okay, so if you were to take the plane and split it in half, and one half, and where you paint it, and you paint one side blue, one side red, then you're going to
Yes.
have there's no other color. There's no
Yes.
way for there to be a space in between those two
Oh,
colors.
absolutely. So each point is either red or blue.
Right. So I think I don't know how to how to write that down to say pigeonhole principle, but I think that's what it's supposed to. That's what the principle is showing. Is that since there's no other color, so the colors are the pigeonholes, and since there's no third color, they must always have 2 points of the same color.
But why 1 inch apart? Why not 2, not 5 inches?
I'm not sure about that though. If the exactly 1 inch part was gone though, it would prove the find 2 points of the same color. I guess next to each other.
How about 3 inches?
But so what does that mean by 3 inches? Like 1
Well,
inch?
imagine that you have a ruler. We have an infinite plane, and you have a ruler. Each point on this plane is either red or blue. There are infinitely many points. You can color your points. You can use any pattern to color your plane. And you have a ruler. I ask the following question. Is it always possible to find 2 points 2020 inches apart? Or 1 inch apart, or 5 inches apart?
It seems self-explanatory that it could be any distance apart. It could be 1 inch apart, 1 point. There be colors that are 1.1 inch apart. I think it might work for all.
So the answer, from your point of view, the answer is yes, no matter what we put here, 1 inch or 5 inches, correct?
I think so, maybe.
But how would you justify?
I mean, I don't know. It just seems obvious. I'm not sure.
Why is it obvious? Imagine.
Well, because there's only 2 colors. There's no.
So what?
Well, because there can't be anything in between those 2 colors.
That's fine, but imagine that we have an infinitely big chessboard, and the squares are small, smaller than 1 inch. Why is it still possible? How to prove it?
I guess I don't know exactly how to say it in words.
But can you describe somehow?
I'm not really sure.
Okay, anybody else?
I'm not quite sure, but I think there's some, like, I have some sketch of a proof. It may
Yes.
not work.
Okay, yes.
Suppose you have like a point and like it's say color, any arbitrary color from blue or red.
So pick a point. This point is either red or blue. Without loss of generality, we can assume that it is blue. What do we do next?
Then you can draw, so the idea is similar to that, like you draw a circle with the radius of 1 inch.
Okay.
So like if like there's any point on the circumference that is also blue, then you're done.
Excellent.
If it's red, you can use that, like if all points on the circumference is red, you can arbitrarily pick 1 red point, then draw a circle of 1 inch radius as well.
Okay, very good.
And then your intersection will be like red because you know it's like the intersection is on the first circle, so it must be red.
Excellent, absolutely. This is an excellent solution. So pick a point, say blue. We draw a circle of radius 1. If on the circumference we have another blue point, we are done, because the distance between the center, which is a blue point, and this point is 1 inch. Now, case 2, suppose on the circumference there are no blue points. This means that all points are red. Pick any of these red points and draw another circle of the same radius, 1 inch. These 2 circles will have 2 intersection points, which means the distance between the center of the second circle and any of the intersection points will be 1 inch. Folks, do you understand the solution?
So are you drawing this next circle? Is it a circle that's like a circle, and then the next circle is touching the edge of the next circle is touching the circumference of the first
Abraham,
circle, or it's centers?
Abraham, I just pick a point on the circumference and draw a circle of radius 1 around this point, such that this point is the center of this circumference.
Okay. So I'm asking, are the circles tangential or not?
No.
They're sequential.
Bear with me. We have circle number 1, okay? We pick a point on its circumference. This point will be the center of the second circle.
Okay, so the circumference of the second circle is touching the center of the first circle in this case.
Yes.
Okay, that answers my question then. Okay.
Yes. And now these two circles will have two intersection points. Both points will be red. Agree?
Right, yes.
So this center of the second circle is red, and both intersection points are red. We just found 2 points that are both red and 1 inch apart. Point number 1 is the center of the second circle. Point number 2 is one of the intersection points. Does this make sense?
Yeah. I understood once I figure out how the circles are being drawn.
All right.
So I got it. Yeah.
Guys, but my question is, where is pigeonhole principle? There is no pigeonhole principle. Well, guys, here's a much easier approach. Think of an equilateral triangle with each side exactly 1 inch long. Note that we have 3 vertices, correct? If we pick any 2 vertices, the distance between these 2 vertices will be 1 because it's an equilateral triangle. We have 3 vertices, but 2 colors. Colors are pigeonholes. Vertices are pigeons. Since we have more pigeons than pigeonholes, since we have more vertices than colors, there will be 2 vertices of the same color. We are done because the distance between any 2 vertices is 1 inch. Folks, any questions here?
So there are some problems that they're not immediately clear that they're pigeonhole principle, but depending on how you solve them.
Absolutely, that's the whole point. This is the main reason why the pigeonhole principle is so hard to apply. Very often it is absolutely not clear what are pigeons, what are pigeonholes. Here, in order to come up with pigeons, you have to draw an equilateral triangle, which is originally not given. This is the problem. Do you understand the solution?
Yes, the solution makes sense.
That's why I was trying to talk about the triangles, but yeah, I got it.
Okay, let us go over number 7. 51 points were placed in an arbitrary way into the square of side 1. Prove that some 3 of these points can be covered by a circle of radius 1/7. So once again, guys, it's totally unclear what are pigeons, what are pigeonholes here. Do you have any ideas? What do we do?
So the circle of radius 1/7 is smaller than the square.
Yes.
So you could fit it inside of the square.
Yes.
And then you could compare the areas and see if 51 points fits in just the leftover, the subtraction of those 2 areas.
But we can always fit as many points as we want, not necessarily 51. We can put 1,000,000 points. These are points. They do not.
Oh, okay. So the points aren't the same as the area then in this case.
Yeah. So guys, here's how we do it. Step one, remember we need pigeons and pigeonholes. Let us divide the square into 25 smaller squares of side 1/5 inch. We divide each side by 5 equal pieces and split the big square into 25 smaller squares. Observe that we have 51 points but 25 squares. This means that there will be a square that contains at least 3 points. So once again, if in each square, we have 25 squares, if in each square we have only 2 points, the total number of points will be 50, but we have 51. So there will be a square that contains 3 or more points. So now the rest is to find the distance between the center of a small square and any of its corners. So the distance will be 1/10 square plus 1/10 square, the whole thing square root. Because each small square has side 1/5, half of 1/5 is 1/10. So in other words, if we have a small square of side 1/5, the distance between its center and any of its sides is 1/10. Therefore, by Pythagorean theorem, the distance between its center and any of its corners is square root of 1/10 square plus 1/10 square, which is lesser than 1/7. Therefore, any such square can be completely covered by a circle of radius 1/7. This solves the problem.